Okay, in the previous modules, we have talked about different algorithms used for autonomous driving, including localization, perception, planning and control, and so on. And you can see it's a very complex system that combines very many pieces of these algorithms into one machine. So in this module, we're going to talk about how to design the client system to combine all these pieces together and then let these pieces interact smoothly so that the autonomous driving system can provide robustness and reliability for the vehicles. For a client system, we start with an operating system because you have so many different modules and these modules interact. For example, if we look at this simple graph, you have on the upper side of it, you have all these different modules: navigation, localization, path determining, obstacle sensing, and so on. They are all executing on one piece of processor. And then many of these modules actually have strong real-time requirements. For example, for the camera module, if you want to hit 60 frames per second frame rate, you have to make sure that your processing pipeline can finish processing a frame within, for example, 16 milliseconds. Then we need to guarantee that we dedicate enough computing resource for, say, for example, the computing module. And then the processor or this client system will communicate the plan as we talk about the feedback control, motion trajectory plan, and so on, to the control box or the control machine or the spinal cord of this autonomous vehicle. And then how do we make sure that communication is very smooth? That depends on what kind of operating system you use and what kind of hardware you use. So let's start with the operating system. Usually for autonomous vehicle, we use some operating system similar to, say, the robot operating system, ROS. They either use ROS itself or they use a modified version of ROS. So what is ROS? ROS is actually a middle layer software component that combines different parts of the software pieces together. So the main task it provides is communication. For example, if you are a node in ROS, you can publish your results through a topic, and then the different nodes will subscribe the topic. In this example, the publishing node can be a camera, such that each time it has an image, it pushes to the topic. And then the subscription node can be a perception pipeline. It uses the camera information for localization. And it can also be the localization pipeline that uses that image information for positional updates and so on. So both the deep learning pipeline we use the camera information, and the localization pipeline you also use the camera information. You can do this through a topic, and then you can do dedicated service, point-to-point communication as well. So that's the beauty of ROS that provides many different communication mechanisms. But however, we are running these complex systems on a autonomous vehicle, so safety, reliability, those are the utmost important concerns of this vehicle. For the original ROS design, it's easily crashed because it has only one master node. If I'm a hacker, I go into the ROS system, I hack the master node, and the whole system might crash. And then communication sometimes becomes a bottleneck when you have a huge amount of information going in. Because, for example, for multicast, currently the ROS 1.0, they just make multiple copies of the same information and send to everybody. So that would consume a lot of communication bandwidth. And then it's not very secure today because there's no encryption algorithms there, no security protection for the ROS system. So once a hacker enters into the system, it becomes very hard. So usually when we build a operating system for autonomous driving, we take the framework of ROS and then we do a lot of patches or optimizations on top of it. For example, for communication, we can use shared memory instead of multicast, such that we don't need to copy it multiple times. And then we can use what we call the Linux container technology to protect each node, such that if one node is hacked, we make sure that the other nodes are still safe, and so on. So that's about the operating system. Below the operating system, we actually have a hardware platform. If we look at this figure, that's an actual design. On the very left side, we have these sensors, for example, LiDAR, GPS, and so on. And all this information are fed into the computing platform, which consists of multiple machines with CPU and GPU, very powerful machines to do the perception part. And then once we finish with the perception and localization, we feed the motion plan to the canvas or the control box to control different parts of the vehicle. So this is the action part. So let's focusing on the computing platform. that's all the generation 1 autonomous driving. They have similar design for the computing platform. Usually they have a very strong CPU, the highest end Intel server-side CPU for computing. And on top of that, for deep learning and for localization tasks, they offload a lot of workload to the GPUs for acceleration. So they have multiple cards of GPU. So to build a industrial computer like this, usually takes $20,000 to $30,000 to build one. And then it consumes thousands of watts of power at its peak. So if you put this box into a car, it might not be very efficient in terms of power consumption and in terms of cost. But is that actually what you really need to run your autonomous driving workload? So to answer this question, we try to do an experiment, see if we can build a very small, limited operating or autonomous driving system on a mobile device. So we take a Samsung Galaxy cell phone with 4 cores at 2.2 gigahertz and see if we can fit these workloads. So we actually move localization and scene understanding onto this platform. The first thing to consider is that, hey, the other guys use these high-end machines for autonomous driving. If we use low-end machine, we really need to fully utilize the computing resource. And then we look at the computing resource on this device. We have a DSP, and we have a GPU, and then we have 4-core CPU. That's all we have. And then the whole system would only consume about 15 watts of power. Then we do some initial study and find out that, hey, actually on this particular platform, the convolution or the visual understanding part, it's really suitable for the GPU in terms of power consumption and in terms of performance. And then the DSP is very good for feature extraction or the visual tasks. So that's what we did. We then designed a system using the DSP for feature extraction, and then the feature would be fed into the CPU using 2 threads for the localization task. And then we use the GPU for object recognition, and then we use the other 2 hardware threads for planning, control, and obstacle avoidance. Turns out the performance is not bad at all. With this pipeline, we are able to do 25 frames per second. And then for object recognition, we can also do 3 frames per second. Not bad at all, with an average power consumption of only 11 watts. And then with this pipeline, we have built a small vehicle that's able to travel 5 miles per hour on only 11 watts of power. So that's a very strong message that if you can fully utilize heterogeneous computing, you can build a very lightweight machine for autonomous driving. Okay, so that's it for client systems. The takeaway message is that you need an operating system, and then you need to optimize your hardware so that you can build a shippable product for autonomous driving. In the next module, which is the last module of the series, we're going to talk about the cloud platforms.